So we were discussing continuous random variables, and we spent some time talking about the exponential random variable in particular, and how we can use integration to get the CDF from the PDF. Now we turn our attention to possibly one of the most important distributions in all of statistics, which is the normal distribution. There's tons of different data sets that exhibit this type of distribution with a big pileup of data in the center, meaning a lot of the data is near average, and a tail of data going in either direction. So there's high data and low data that kind of balances each other out in a symmetric way, but the farther you go out in both directions on the x-axis, the fewer and fewer data you see. So for example, if you look at the heights of adult males or adult females, you will see overwhelming majority of them clustered near the center, with a few adults that are unusually tall and a few adults that are unusually small. But you would see the same thing if we looked at SAT scores or almost any score of intelligence. You would have the majority of the scores clumped around average, with a tail of scores going in this way. Very few that are high up here and very few that are low down here. Here's an example of SAT scores. This is heights of 14-year-old girls. This is SAT scores. There's a lot of different distributions that have this shape. Even something like flipping a coin. If you flip a coin a whole bunch of times and count the number of heads that you get, the distribution of the number of heads even follows a normal distribution, or at least really closely resembles a normal distribution. So since the normal distribution is symmetric, the mean and the median are in the same place. And the shape is generally described as mound-shaped, unimodal, meaning one peak, and two-tailed. For the purposes of integration, it's got kind of a complicated PDF. So in general, this has the format of e to the negative x squared. That's the general form. When you let the mean equal 0 and you let the standard deviation equal 1, then the PDF simplifies quite a bit to this. Interestingly, the reason why the 1 over radical 2 pi is there is so that the area under the curve will equal 1. Like any PDF, the total area under the curve is supposed to equal 1. Even with this simplified version of the PDF, the problem is that a function of this form does not have a antiderivative. So there's no way to find the CDF like we did for exponential. So over the years, many different kinds of numerical integration techniques have been used to obtain values of the CDF by integrating this PDF numerically. So because there's no closed form of the CDF, there's a couple important numbers that are usually memorized about the normal distribution, and that's the 68, 95, 99.7 rule, which is sometimes referred to as the empirical rule. So in any set of data following a normal distribution, whether it's the heights of adult males or SAT scores or whatever, if it follows a normal distribution, 68% of the data will be within one standard deviation of the mean. And so when we say within, that means from one standard deviation below the mean to one standard deviation above the mean. And perhaps the most important number here is 95%. 95% of the data will be within two standard deviations of the mean. So that's from the mean minus 2 standard deviations to the mean plus 2 standard deviations. And 99.7% of the data, almost all the data, but not quite, because there's a little tiny sliver of a tail that continues to negative infinity, and there's a little tiny sliver of a tail that continues to positive infinity. But 99.7% of the data in any normal distribution will be from 3 standard deviations below the mean to 3 standard deviations above the mean. Another interesting fact about this curve that we could actually prove in this class, I can't in my lower level stats class, but if you take the second derivative of the PDF and you set it equal to 0, you might remember from calculus class, setting the second derivative equal to 0 is how we identify an inflection point. If you take the second derivative of this and set it equal to 0, you get that the inflection point is exactly at the mean plus sigma and exactly at the mean minus sigma. So I use that a lot to, even if I don't convey the notion of the calculus behind it, I use that a lot to locate my standard deviation marks. So I try to draw this curve as best I can, and then where the inflection changes from being concave down to being concave up, that's the one standard deviation mark above the mean. And if you've drawn it symmetrically, you have a corresponding point over here, which is the one standard deviation mark below the mean. And then once you have an idea what the distance of one standard deviation is, then you can mark that distance off again for two standard deviations and so on. So that's kind of helpful when and if you're drawing this curve by hand. So this breaks it down a little bit further. And I used to have, back before we had calculators that did all this, I shouldn't say before we had calculators, but before I had a lot of students that had calculators that did all this, I used to have students memorize this somewhat more complicated chart. So it's got the 68, 95, 99.7, but then it's got a lot of other numbers derived from the 68, 95, 99.7. For example, because the curve is symmetric, the 68% is split up 34% here and 34% here. And the 95% is split up 47.5% here and 47.5% here, which means that this little chunk here is 47.5% minus 34%, which is 13.5%. So used to have students memorize this, but nowadays most of the calculations involving the normal curve we're going to do on our calculator. So usually on problems involving the normal distribution, we're going to turn the raw data of the problem into a z-score. So if we turn it into a z-score by subtracting the mean and dividing by the standard deviation, then we will be able to use something that's referred to as the standard normal distribution or the standard normal table to look up answers to basically any problem involving the normal distribution. So here's an example. Heights of adult males in the U.S. follow a normal distribution with a mean of 69 inches and a standard deviation of 3 inches. What percent of adult males in the U.S. are shorter than 62.2 inches? So the first thing we need to do is turn the 62.2 inches into a z-score by subtracting the mean and dividing by the standard deviation. So when we just subtract the mean, that tells us that 62.2 inches is 6.8 inches below average. But then when we divide by the standard deviation, the significance of this number is that the 62.2 inches is 2.2 standard deviations below average. So the z-score transforms our original data into standard deviation units. So a height of 62.2 inches is 2.27 standard deviations below the mean. And this 2.27, this negative 2.27, is what we're going to look up on a table. So before I get too much into this table, let me just show you there's a couple different places you can find this table. Number one, if you're working on the homework, any problem that's about the normal distribution is going to have a link somewhere for the appendix of tables. And if I zoom in a little bit here, first is binomial and then is Poisson. First is binomial, then is Poisson, and then we have the standard normal distribution. So that's the same table that I'm showing here in the notes. The other way you can get there if you want to download a PDF is from our web page. Up at the top, I have a link for standard normal curve areas, and you can click on that, and that's a PDF of the exact same table. So back to where we were. We're trying to look up a z-score of negative 2.27. So we find the row for a z-score of negative 2.2, and then the column for '07. And the negative 2.2 and the '07, that combined is a z-score of negative 2.27. And where those intersect is our probability, 0.116, meaning about 1% of the normal curve. So a z-score of negative 2.2 would be down here somewhere. And so this 0.116 is telling us that about 1% of the normal curve or of the normal distribution is below a z-score of negative 2.27. And if our z-score had been negative 2.26, then our answer would be 0.0119. If our z-score was negative 2.25, then our answer would be 0.0112. So we're looking at a z-score in the margins of the table, and then the probability or proportion or the area under the normal curve to the left of that z-score is reported to us in the table. So the proportion of the normal curve that's less than a z-score of negative 2.27 is 0.116. So I like writing this as a probability statement, first in terms of the raw data, and then a probability statement in terms of the z-score, and then the answer that I get from the table. Very easy to do this on the calculator. On the calculator, if you press second vars, and the second item on the list is normal CDF. We will use this a lot. And the only thing that's a little bit tricky for some students is if we want the probability of being less of a z-score less than negative 2.27, then less than that means that our starting point is negative infinity. And by default, the calculator puts a number like this for negative infinity, but usually I just put negative some big number for the lower bound. And then the upper bound would be my z-score, negative 2.27. And the calculator gives me the exact same 0.116 that was on the table. Where were we at? The same 0.116 that was on the table right there. Notice also, because we subtracted the mean and divided by the standard deviation, we have on here the mean set to 0 and the standard deviation set to 1. So you always want the mean at 0 and the standard deviation 1 if the number you're putting in here is a z-score. Okay, so when we're doing probability of z less than some number, the lower bound is negative infinity, and the upper bound is our z-score. If we happen to be doing a greater than, then the probability of z greater than some number, then the lower bound would be our z-score, and the upper bound would be infinity. So anyways, this is the way it looks like on the calculator. And notice when I hit paste on the calculator, it automatically puts in the 0 and the 1 for the mean and the standard deviation. But even if you leave that off, it's assumed to be 0 and 1. Okay, and I usually leave that as a 4-digit decimal number just because for many, many decades, we've been used to 4-digit decimal numbers off of this table. If you want to change that to a percent and say 1.16%, that's fine. Another little cool thing on the calculator is you can set up the calculator to draw this probability or this proportion or this area. But the trick is you first need to set up your axes. So I'm going to press the window button, and this is only if you want to graph the normal curve on the calculator. Pressing the window button, I'm going to make my x go from -4 to +4 because 4 standard deviations above and below 0 is a lot. And then for my x max, I'm just going to put 0.5. So my y max. So the x-axis is going from a minimum of -4 to a maximum of +4. My y-axis is going from a minimum of 0 to a maximum of 0.5. And then if you do second vars draw, the first item is shade norm. So you can say shade the normal curve from negative infinity to negative 2.27 with a mean of 0 and a standard deviation of 1. And here's a beautiful picture of a normal curve with the appropriate area shaded. And then it's even going to tell us that we went from a low of negative infinity to a high of negative 2.27, area 0.116. So there's a bunch of ways of getting that 0.116. You don't have to do it this way, but I kind of like this because I like the visualization of the normal curve. Continuing with our example, what proportion of adult males in the U.S. are shorter than 72.9 inches? So, same routine. Turn the 72.9 inches into a Z-score. Look the Z-score up on the table. So here's the portion of the table for 1.3, and our Z-score was 1.3 exactly, so we're going to say 1.30, and the proportion from the table is 9032, meaning about 90%, of adult males are shorter than 72.9 inches. Okay, or normal CDF on the calculator, second vars, normal CDF. Okay, no, let's try this again. Second vars, normal CDF from negative infinity to 1.3. And that's the same 9032 that we got on the table right there. What proportion of adult males are taller? Notice I'm underlining the word taller than 73.1 inches. So you turn the 73.1 inches into a Z-score, which is 1.37. And if you look up 1.37 on the table, you get 91%. So here's 1.37 on the table, 91%, 0.9147. But this picture that's at the very top of the table is a reminder for us that the number we're getting out of the table is the proportion of the normal curve that's below that Z-score. But in this case, we want the proportion of the normal curve that's above this Z-score because it said taller. So we're going to have to do 1 minus this number we get off of the table, which is about 8.5%. So that 1 minus operation is something you have to do when there's a greater than sign and when you're looking it up on the table. If you're using the calculator, then there's no reason to do the 1 minus operation. You just have to specify your bounds on the integration, so to speak. So now if I'm going above 1.37, then my starting point is 1.37 and my ending point is infinity, or just some huge number. And there's the 8.5% number that we got from subtracting over here. A lot of times we'll have a problem with between. So between 70.77 inches and 71.88 inches. So now you have to turn both of those heights, both of those raw numbers into Z-scores. And then you have to look up both of those Z-scores. I got a 0.59 and a 0.96. Look up both of those Z-scores on the table, 0.59 and 0.96. So 0.59 gives me this proportion, which I've written down here, and then 0.96 gives me this proportion on the table, which I've written down there, and then you subtract those numbers from the table, and you get this, which means about 10%, maybe 11% of adult males are between 70.77 inches and 71.88 inches. Very common mistake students make is they'll calculate the two Z-scores and then subtract the Z-scores. That's wrong. After you calculate the Z-scores, you look up both of the Z-scores on the table, and then you subtract the numbers that you got from the table. Of course, if you're doing this on the calculator, you don't have to do all that. You just put the Z-scores in. When the problem is a between problem, you just put the Z-scores in, 0.59 and 0.96, put those in as your upper and lower bound, and there's no subtraction necessary. And I could also do a shade norm on that. Let me do clear draw first, and then a shade norm, just to see the little sliver of 11% that we're talking about, from a z-score of 0.59 to a z-score of 0.96. Let's see what that looks like shaded. So here's our beautiful normal curve, and that's the little sliver of the normal curve we're talking about, from a z-score of 0.59 to a z-score of 0.96 is about 11% of the normal curve, or in this case, about 11% of adult male heights. Okay, so now what if we have to do all of that backwards? In other words, on all of these problems, let's go back to the first problem. On all of these problems, we have taken a height as a raw data, turned it into a z-score, and then looked at that z-score on the table, and then reported the proportion or the percentage from the table. What if we do all that backwards? What if they give us the proportion? If they give us the proportion, from that we should be able to figure out the z-score, and from the z-score we should be able to figure out the raw number. So this is kind of a common problem. The question is, what height represents the 95th percentile? So now we are being given a percent, 95th percentile, and we are being asked for the male height. So first, we have to find the z-score on the table that would give us as close as we can to 95%, which as a decimal on the table would be 9500. And the closest you're going to get is those two numbers there. So it's kind of a toss-up if I should be using a z-score of 1.64 or a z-score of 1.65. In reality, I could live with either one of those, 1.64 or 1.65. Or if you use technology, you can get the exact z-score. So back to the calculator, if we do inverse norm, so that's second vars, and then the third item down is inverse norm, and tell it the area is 95%, the calculator will tell us what z-score has 95% of the data below it. And usually statisticians call this number 1.645. There's a long story why 3 digits on the z-scores, but 1.645 is usually kind of generally accepted. So now that we know the z-score is 1.645, and by the way, we still know that the average of all male heights is 69, and we still know the standard deviation is 3. What we don't know, what we were asked for, is the adult male height that corresponds to the 95th percentile. So the adult male height that corresponds to a z-score of 1.645. So solve this little equation algebraically, and you get about 73.9 inches. If you are algebraically challenged, you can use a slight modification of inverse norm. Check this out. Second vars inverse norm, still with the 0.95%. But now if you tell it that our mean is 69 and you tell it that our standard deviation is 3, the calculator will do the backwards transformation for you and tell you that the male height that we're looking for is 73.9 inches. So that's pretty cool if you don't want to solve this problem up here algebraically. But either way, we're going to get an answer of about 73.9 inches. If you round it off too much and use a z-score like 1.6, then we would have a problem. But anyways, that's it for the world of the normal distribution, and I'm hoping you should be able to tackle the homework on all that now.